All right, now we're starting. Okay, so Jim, again, just quickly tell us a little bit about your background with climate because it's particularly interesting and you're very active. So that's a bit of an exception.
Yeah, I said I grew up as an electrical engineer and worked for 39 years in the building materials business, one of the big international groups. Ended up as group technical advisor to the CEO. And strangely, in my last year in the job before retiring, the board wanted a report on climate change and what it meant and so on, and more in the commercial sense, what it meant. So I did a report, and it certainly, even from then, I began to see there is another side to the story. And that, fueled an interest in climate change. And I've been studying it ever since the 15 years since I retired. And, it reached a stage where I could see more and more that what's out there in the public domain and in the media is not truth. It's greatly exaggerated and biased. So on that basis, a couple of us got together in 2015 and sat down, look, and say, we really need to start telling the world what climate change is about objectively. And we formed a small group called the Irish Climate Science Forum. And we started and got lecturers from all over the world, including you, David, to give talks to our group. And now we of course originally did it in a hotel room, but now it's on Zoom, and we have a hugely international audience. And we get in the top guys, the top independent, objective guys, and they give us the latest science, and we disseminate that widely. We don't have any political agenda. We're not subsidized or financed by any oil groups or any sector. We do it literally out of our own pockets, and it's a minuscule budget. But I think we are really reaching out, and all our lectures can be seen on our website, which is called icsf.ie, and there's all our lectures are on that. In fact, I think it's the best compendium of climate science lectures up to now, David. And so it's a fascinating topic, and I think the world is beginning. Even the fact that you're holding these classes, the world is beginning to open its eyes and say, "Are we being hoodwinked and all of this stuff?" And there, people in Ireland now, they can see the adverse economic effects of the crazy policies. Actually prohibiting an LNG import terminal, refusing permission to new gas-fired power stations, limiting the capacity of Dublin Airport, all this blooming nonsense. And really, and when you analyze it, and as you'll explain, David, the impact of CO2 is pretty well zilch on climate compared to all the other aspects, solar, clouds, whatever. But and particularly the agricultural gases are, despite what everybody says they're being enormously potent, is complete rubbish.
Right.
So we are fighting the good cause, and we've got a good lot of abuse along the way because of that. But I think people are beginning to respect now. There is a different view, and it's important, David, that they are educated, and that the message seeps out, and eventually that our politicians and the pressure groups begin to look. Let's be more reasonable. Let's of course be sustainable. Let's we are a planet of a growing population, and resources of all kinds are becoming scarce, and we need to be careful and prudent and recycle and develop new technology. But let's be sensible about the climate.
Very good. I'm sure you're paid by big oil. I'm sure you're just getting huge amounts of money by giant oil companies. You're not fooling me for a minute, Jim. I get accused of the same stuff every day. So I want to give an overview, but quickly, let's just go around the room. Who is Lenovo 256? Is that, I don't know your name. can you unmute and say hi? Or if not, I'll move on. What's your name?
Got me? My name's Bill Perry.
Bill.
Yeah,
Great.
Bill from Plymouth.
Plymouth. Very nice.
Yes, UK,
All right.
UK column territory.
And your background and interests?
I worked in electronics in the university in Cambridge for a while, and now I've retired, trying to take an interest in the world a bit more than usual.
So many different interests.
Indeed, yes.
All right, great. Let's go on to Louise.
Hi, can you hear me?
Yes.
Yeah. So I'm in central Scotland, and I am a wife, mother. I'm an avid gardener and total weather watcher. I love to do walking because obviously in Scotland you can walk lots and lots of different places. And really, I'm so interested in what's happening in the world at the moment. And I do like to read about both sides of the argument, but I think you've got to go down the middle path initially and then make up your mind. But I do believe that we shouldn't be needlessly polluting. But, we all have to live our lives too.
Okay, great. Let's go to Kevin. Where are you and your background and interests? Kevin, you there?
Yes, just unmuted now. Okay, so I'm from a place in West Yorkshire. Okay, and so currently I sort of work full time in the NHS in a clinical role. So yeah, I won't go too much into it, to be honest with you. But
okay.
In interest wise, probably a wide variety of interests. Interested in sort of the different topics and ways that we lie to on basically on virtually every topic. And I think that's about it, really.
Okay, great. James, unmute.
Oh, sorry. Hi, I'm James. I do apologize for not having a camera. My laptop is broken. I'll sort that out for next week. I live in Portugal with two crazy Irish setters that are just coming, 3 next month. So 5 minutes from the Atlantic Ocean. My background's software engineering. I left school at 16, being dyslexic, which got me into systems thinking, language, neuroscience, and persuasion engineering. And something smells around what's happening at the moment. So I'm very interested to learn more. I've got very little experience in climate change, but I'm a quick learner.
Great. All right, we'll go to Elizabeth. And then Lana after Elizabeth.
Hi, I'm Elizabeth Pang. I'm a holistic therapist and I live in North Yorkshire in England. I was part of the anti-fracking movement here in North Yorkshire, and that started to morph into the climate change narrative. And initially I swallowed that sort of hook, line and sinker. And then something triggered me and I realized that we were being completely lied to. And so stopped believing anything at all. And now I want to understand the truth, please.
I will try to be less wrong than I was last week. That's about all I can do. Okay. Great. And Lana?
Yeah, hi there. I'm in Croatia at the moment. I live here by the sea as well.
Croatia?
In Croatia.
Dubrovnik?
No, it's near to Rijeka, north part of Adriatic.
Okay.
I come from Zagreb. I was born in Zagreb, but at early age I left to UK. I spent 35 years in London, in central London, working, studying horticulture, and then working in retail, and afterwards in landscaping. So I've been 20 years. I had my own business, landscaping for rich people in Chelsea and all around the central London. So I'm a kind of a grower at heart. And while studying, we were told that to increase the yield, we need to increase the CO2 levels. So when
That's
the
right.
whole narrative started, I thought this is nonsense then, because if we need more yield, we need more CO2. So that can't be a problem and that can't kill us. And I don't think we are the reason for the whole problem, although I do believe that our practices are very wrong. And having traveled all around the world, well, to many places, I've seen the accumulation of the, plastic and the rubbish and people not being aware at all what to do with it and how to deal with it. And I still believe it's not really properly dealt anywhere with the consumables that we all consume, some more, some less. So having to hear you at the UK column, yeah, I just thought I'll join this course and just get more knowledgeable because people around me and lots of people believe that we are the problem and the climate is seriously changing. And my view is kind of different, and it's much beyond us and much bigger than us to make it so small and just put it all that we are the cause, because I don't think we are. Equally with oil, I don't know what are the views on oil. I like to, learn more about oil. Is it so detrimental? Because some say that it's the biggest after the seas. It's the biggest fluid in the earth, and they told us it's scarce. And also, if we are given this as an energy, why that kind of energy would kill us? So, I just really like to know more about all of it, basically.
You're asking questions. Good. I'm going to put a link here in the chat, and most people here will be interested to read that. So you could click on it and then read it later. Fantastic. Love it. Simon? Are you with us, Simon?
Hello, can you hear me?
Yes.
Good. Well, I live in southeast London. I've spent 25 years professionally as an economist working for the government.
Oh.
And now I'm retired. And I've always felt that it was inherently unlikely that by ceasing to consume carbon fuels that we would somehow avert some major catastrophe, or indeed that the benefits of doing that would even exceed the costs, which already seem to be quite substantial.
Right.
I've never really I've been on the periphery of climate policies, but I've never really addressed myself completely to the scientific issues involved in it.
Okay.
So I don't feel confident in my assertions, and I would like to be more confident and understand better what impact CO2 actually does have on the climate.
Or it doesn't do. So you're a crazy person who believes in cost benefit analysis?
Yeah,
oh my
yes.
God. That's such a fringe view.
Yes, I
Don't know
know.
where you got that.
Absolutely.
Nothing to do with reality these days. All right. Let's go to Christian.
Yes, hello. My name is Christian. I live in Denmark, or in
Copenhagen?
the countryside,
Oh, the countryside.
which is very nice. My background is mechanical engineering, and I worked as an engineer with project management, sales, business management for a number of years until about 5 years ago. Then I stopped doing that. During the Corona pandemic, I started to ask questions to myself and try to learn what is really going on in this world. You could say I seek the truth, and maybe I'll never find it, but at least I've found very good support in the news by the UK column, and obviously through that channel I heard about this course, and as everybody's talking about climate and scaring us about doomsday and everything, I thought it would be very good to get some proper real science knowledge
Okay, good.
as part of my, call it training or journey to find out what is really going on. So yeah, that's me.
Great. The only thing I think schools should teach is critical thinking, but it's the one thing they don't teach.
Correct.
Okay. And Lana, by the way, Lana, the most volume fluid on Earth is rock, molten rock at the center of the Earth. Obviously, that's overwhelms water by a lot. But I wonder if oil is number 3. It certainly could be. Teresa.
Hello. I live in the southwest of England, but not quite as far down as Plymouth. And I work as a homeopath. And I started watching the UK column, I don't know, 2 or 3 years ago, whenever. And clearly I was most interested in the health sort of end of things, because the vaccination, homeopaths have a slightly different view on vaccination, let's just say, than where the money goes. And it's good to get the rest of the background to back up how I've been working for, feeling and understanding for a long time. I know that back in the 1950s, I think it was, they started trying to seed clouds and change things. So I reckon that by now, which is 70 years later, there's probably a lot going on that we don't know about in similar ways. I don't know. And I'm here to, find how you see it. That's about all for me.
Follow the money is the right approach. And Martin, last one, I think.
Can you hear me, David?
Yes.
Oh, thank you. Yeah, hi, I'm Martin. I live in London in the UK, and I've been following UK column for a number of years now. My background is in construction or building, as you say here in the UK, doing carpentry. But I've always been interested in environmental stuff. I come from a west of Ireland tradition of small holding farmer fishermen. And it's extremely important in that thing, like to look after the land and to look after whatever you've got around you. Because believe me, in the west of Ireland, you don't have much. Anyway, yeah, I used to think like everybody else up until I went online in 2008. And since then, I don't have a television, I don't listen to TV, radio, or newspapers. And I've completely redone all my education and everything I thought I knew in 2008. And realized basically it's just been one big hoax. So I think there is fodder for the masses and there's what's really going on. That's it, really. I could say a lot more, but I'm going to keep the short story short. Okay.
Thank you. Okay, perfect. We're all on a journey. We're all trying to learn, and we just want to know where it goes, what's really going on. We don't really care what causes what. We just want to find out, right? That's what scientists do. And my hero in science is Richard Feynman. Who knows Richard Feynman? Who's heard of Richard Feynman? Anybody? A few people? Not so much. Yes. A few people. So Richard Feynman was a scientist who worked on quantum electrodynamics and got the Nobel Prize for it. He worked on the Manhattan Project, and he taught physics for many years at Caltech. And he's written many wonderful books and given many lectures. And I raised my children reading Richard Feynman to them. And I recommend this school of Richard Feynman to anyone, especially for parents trying to teach kids, because it's all about finding things out, finding out how things really work without having an agenda, just try to learn what's going on. Now, in this class, there's going to be 3 levels of goals. I have sort of 3 possible goals that one could have from this class. And one is just self-enrichment, as many people have expressed. Just learning for yourself and trying to understand the world, ask questions. Dialogue is very good for this, because you can read anything. In fact, you could watch Tom Nelson's channel and see completely conflicting scientific explanations of all kinds of things about climate. And through conversation and analysis, we try to sort some of this stuff out and throw out what doesn't really pass a simple test and try to keep what does. So personal, if you're here for personal reasons to kind of just increase your own knowledge, you're going to win. This is going to be well worth your time and money. If you're here, on the other hand, the second thing would be to help convince other people and talk with other people. That's going to lose. I can guarantee it, because they did not make up their minds based on data and reason. And so no amount of data and reason is going to help. And they're going to just say, well, are you a climate scientist? How many papers have you published? Who listens to you? Oh, you're going to a class by a climate guy? Oh, I'm sure he's telling you the real thing the way it really is. So that there's just, and then they're just going to say, well, you know what? I'm going to go with, the United Nations, Scientific American, the American Geophysical Union, the London Science Society, the governments, and on and on and on. And I am just, I appreciate you spending your time on the internet, in the internet dungeons, learning all these fascinating things, but you're just not going to convince anybody, of this stuff, because it's not rational, it's religious. And in fact, I've always said this is an identity issue. They can't change their minds, because if they did, their friends would defriend them. And I have certainly lived through that. I have lost many friends who've decided that I'm toxic because I talk about science, and they are only interested in community and identity and being positive for the environment so they can have a Tesla and they can use wind power. That's, we must destroy the environment to save it, apparently. And so people have pretty much lost their minds based on a story that's fascinating how it got started. We'll talk a little bit about that at some point. But the Rockefeller family name keeps coming up over and over and over. And in the Mighty Networks, in the network, I posted the first film by Jakob Nordengard about the Rockefeller story, which is just fascinating. So it's kind of the origin story of the environmental movement and how they're using it against us. And there's more to come. The third level where we might be able to do something is to actually change the world a bit and change minds. And that will take a lot more. That will take more of a group, like what Jim is doing. Jim is doing great work with, I don't know how many people on your mailing list, but thousands, right? I think you're muted, but I think it's, it's thousands of people you're having an influence on, right? And the conversations are important. And so it's this kind of, working together where we might be able to make a difference. And for me, that would mean that this whole thing is just the seed of a much bigger thing that grows and grows and grows and turns into something that gets respected and people listen to, and media people want to interview and talk about. And or maybe we'll join one. There are several already. There's certainly Clintel, and I'm a member of both Clintel and the CO2 Coalition. So there's just something possible that we'll talk about in about 8 or 10 weeks about how we could take this up to the next level. I have a few ideas, but that's a conversation for later. But out on your own, out in the world, if you asked me to just come every week and you bring me the arguments that people are using against you, and you just help me, I'll help you shoot them down one by one by one. Hottest year on record, storms, extreme weather, all that stuff. We could just shoot this, just whack-a-mole, just whacking these things down, and it will not change anything. It just makes you more frustrated, and it annoys the people who have the red maps because they're thrilled about their red maps. They love getting the attention of the liberal crowd because they're putting up their red maps and sounding the alarm. So it's just not a useful use of time to keep whacking these moles, because they'll just keep springing up. They don't care. You know, it causes, you know, asthma or acne or, you know, paraplegia or whatever, you know, dandruff, whatever it causes, the autism, they're not going to listen to reason about it. They're just going to keep getting attention. So, and that keeps them in their tribe and it keeps them safe. I will, so I want to now just use that as just a sort of a basis for this. Use this for yourself and your self-enlightenment. Use it to think about how we could strengthen this and take it much bigger and much more effective, and really get out and what would it take to make a difference. And don't be in the middle where you're just hand to hand fighting with people who will not be beaten. They must be right. That is their priority. So if you think about where our journey, all of us are here because we are people who realize when we're wrong, we want to understand how we went wrong and what is right or what is less wrong, and we want to correct. Okay, that's less than 5% of the population. 5% of the population, 95% of the population would rather defend their position and feel self-righteous than give up their position and try to learn something new. And I have learned that over the years after having written this book. I showed this on with on the UK column thing talk. And this book is about 3 things. I wrote this when I was sort of 26, 27 years old, and I wanted to sort of lay out a path for my life because I was an environmentalist and I wanted to talk about conservation. And so this was about the population explosion, which probably right there, you know, basically the population explosion is going to kill everybody and it's going to be a disaster. And we're going to have to, and I was very serious about the population bomb. And I know Paul Ehrlich, I knew him pretty well. I was at Stanford and I spent a bunch of time with Paul. And then the second thing was about diet and being vegan and how you should be vegan. I've been vegan for 40 years, but how being vegan is more healthy. And then the other one, the last one, is climate change and how, you know, humans are destroying the climate. All 3 of those are wrong. Okay, I have to admit that pretty much every word in this book, even though it's beautifully produced, is wrong. And I just had to dive into that. And so in 2015, I spent a year on climate working actually with a mentor of mine who helped me understand critical thinking. And sort of my education began in 2015. And I started writing about it and started making noise and learning and losing friends. And it's just been a fascinating journey, because every time I write something about climate science, I look at it later and I go, yeah, you didn't quite understand that. You explained it pretty well, but you didn't fundamentally understand it. So the guy I think who does really understand it is Javier Vinos. And he has written 2 books. One of them I can't hold up because I don't have it yet, but it'll be here. Anybody have the Vinos book in hard copy yet, or in paper? You have one, Teresa? Wow, you have the paper book? Fantastic, amazing. Mine is coming. They're printing it. I think about 4 people had it on Monday. By the way, this is a good class. Thursday, this size class is excellent. So I think if you can stay Thursdays, you should. Tuesday is just too big, and probably we'll get some Tuesday people coming here. But Javier Vinos is a guy who I've gotten to know over the last year. I've read his material. I've spent hundreds of hours with his material. I've really worked on understanding it. I've read the book twice, and I want to try to just be less wrong every week about my mental concept of what drives the climate. So maybe I'm a few steps ahead of you, but we can all learn and we can all ask questions. And I got good questions last week and or last classes, and that's kind of how we evolve our mental models, our thinking about the world. And if this goes well, by the way, I may introduce another class on critical thinking in general. but let's just apply it to climate change now, or what drives our climate. So with that, I'll just go into a kind of a sort of overview of where I think the class might go. These are some of the, whoops, here we go. Topics that I'm interested in over the next 8 weeks. And I'm not committing to this, but today we'll do the history of the Earth and the atmosphere. Everybody can see my screen okay? All right.
Yep.
When I'm sharing, I don't really see you. So if you need to interrupt me, just unmute and tell me I'm screwing up or something. Next week, I've got a big lecture on average Earth temperature. And then everybody, I assume, has seen my talk with Mike on UK Column, right? I assume. Now, there's another thing to see if you're in the network, in the community, and that's my video that's on my website called climatecurious.com. So the first video there, and I've also reposted it in the community, that will be sort of a good basis for, I would like everybody to have seen that. And that's called Climate Science 101, I think. And that's on my website, and it's on the community site. My website is climatecurious.com. So then we'll talk about temperature gradients, because that's the driver. That's 90% of the whole thing in a nutshell. We will spend some time on the greenhouse effect, just so we don't say dumb things about it, because it's ridiculously complicated. And then Milankovitch cycles probably, although I may change these things around, the sun and what's going on with the sun, water vapor and clouds. So you can see this really is climate science. I'm not doing any, I'm not going to talk about energy. I'm not going to talk about politics. We're doing climate science. Heat versus temperature, we might cover at that point. I'm kind of just sort of staying a few lectures ahead, so we won't I'm not going to promise any of this. The meridional heat pump is the big one, and this is kind of why Javier wrote his book. And this is if you remember one thing from this entire course, it's going to be on the heat pump and how the heat pump generally works without too much detail. That's going to be a critical class. And then we may talk more about how CO2 is not driving climate. We may not, I'm not sure. And then we've got modern climate, so that you have some context for what's going on, and then a lesson on future climate. And again, these things may change. And today I want to go through now. I've got, I've got 45 minutes to go through the history of the Earth and its atmosphere for the last 4.5 billion years. So if everybody's okay with that, if anybody has any comments or questions, now would be fine if you do, based on, what we've said so far. Anything, anybody?
Looks interesting. I'm excited. That's good.
Okay, great. And yeah, make sure to communicate with me, especially in the community site. Here, you can see the community site. If you're not in here, you should be in here. One thing that's cool is that people have put their pictures and a little blurb about themselves, so you can see. I would consider myself a critical thinker, a conspiracy theorist. This is all good. So people have put little blurbs about themselves. You do that in your member profile. In your personal settings, you have an edit profile, and then you can put some text in there, and that's nice because it tells other people more about you. And then also, down here we have a community where I want people to just get to know each other, and people just haven't started yet, but whatever you're working on, whatever you're doing, whatever needs you have or things you might want to collaborate with or need some help or resources, let's use it to get to know each other and help each other. And then we have climate general topics and then questions and answers. This will be mostly questions for me. Very useful site, and we'll have access to it for at least the next 12 weeks and then probably later. I haven't decided what we'll do after the class. 4.6 billion years ago, let's go back. Let's go back about 8 billion years ago. There were a bunch of stars here. I think the galaxy was around then. And those stars, one by one, exploded in supernova, and several of them formed a dust cloud that became a stellar nursery. We don't know how many. But it's probably likely not too many because stars tend to be separated by a couple light years at least from each other. So let's say a handful of stars exploded, created a dust cloud, and that dust cloud is rock dust and gas is the primordial ingredients of the Earth. And it's very important to understand that this is a result of supernova because every element above carbon, heavier than carbon, was created in those supernova. They were not present before that. And that's all of the metals, the aluminums, iron, gold, silver, all the, iodine, all these lots of things that we are made of are all created in those supernova, that some of which started to go around in a circle or start to accrete and attract each other. At some point when there was a core, and most of this material is hydrogen and helium, just because those two things dominate, those two elements dominate, they started to get weight, some mass, and around that center of that mass started a bunch of material spinning in a disk. And that's the core of our sun and its formation disk. And the interesting thing about the disk is that for probably random reasons, I want you to imagine that these supernova that exploded were very chaotic, right? There's no way to predict anything. But after they exploded, the only thing working at that point was gravity, right? So if you knew the position and velocity and direction of every single atom in that dust cloud, you could follow it pretty deterministically just by following its path via gravity, and which turned into angular momentum, which gave us our Earth and its climate and pretty much everything we see today. So I'm going to talk a lot about momentum because after that initial chaotic event, everything was just driven by one force, and that's gravity. Now there's heat and thermodynamics and stuff that's coming, but I want you to think about this disk. And what's interesting about it is that the inner parts of the center of the disk was hydrogen and helium. And that, as it got more massive, attracted more hydrogen and helium. And around that was a ring of rock and dust. And after that was gas, a big ring of gas, of methane, certainly hydrogen and helium, but also nitrogen and other gases were in a big ring. And so those rings had little eddies in them. Again, this is all just momentum, where enough stuff clumped together to have its own attraction to nearby stuff. And those eddies became the planets. And so the first 4 planets in our solar system are rocky because of that inner ring of rocks and dust. The outer ring of gases created the gas giants. And those two things were already separated early before the planets formed. And every one of those eddies became a planet. And with an eddy, pretty much anything at that distance away from the sun managed to get sucked into each of the planets. It'd be interesting to see an animation of this. I've never seen one. And that early Earth, first of all, has attracted so much stuff that it's gotten very hot, 4,000 degrees. And the length of day here is unknown because the Earth is very small at this point. So just before this, 4.6 billion years ago, a giant asteroid or a giant small planet thing crashed into Earth. There was a huge explosion, and that material was ejected out of there. The Earth remained in a relatively lumpy shape, and around it was a disk of material, and that disk of material became the moon. So one of the interesting processes here is that disks of material at the same distance from a body tend to come around and clump together and form little planets, moons, and asteroids and things. So the moon was already in motion here, or at this time was kind of a ring around the Earth, and the Earth is pretty small. And so now I'm going to start the animation. I'm going to go through 4 million years in about 30 minutes. But you see the length of day is 4 hours and it's down to 700 degrees C. So what's going on? It's small. Right now, it's about half the size that the Earth is. And I want you to think about the atmosphere. First of all, you see all these numbers over here? All these numbers are wrong. I guarantee you all these numbers are wrong. There's no way we have enough evidence here on Earth today to figure out what these numbers are with this amount of precision. Even just, you know, this is 2 decimals of 2 digits of precision. It's impossible, right? So and there's 20 different videos like this online. This was the one I like. And they all say different things because there's evidence is very sketchy. There isn't much of it. Nobody has any budget to go out and drill enough cores and holes to try to figure this out. There's just, you know, there's just not enough funding. So this is pretty good, you know, guesswork, and it stays very high level of guesswork for the first 3 billion years for sure. And even we don't know much about what happened 2,000 years ago, let alone 2 billion. So keep in mind, these numbers are rough and some of them could be very, very wrong. Although the length of day is probably pretty close. What's happening here now for the next, these are impacts here. For the next 500 million years, the Earth has no atmosphere and no magnetosphere and no ozone. So anything attracted to the Earth just adds to it. So this is an accretive phase during which all these impacts add up and the Earth gets to its pretty close to present size. So it's growing and slowing down in the same way that a skater slows down as she puts her arms out. And just through friction with the solar wind, we're always getting slower. Rate of rotation is always slowing down. We talk about that in a little while. So here we are at 4 billion years, and it's pretty much still, well, here we're at 72 degrees. So let me go back a minute where things are very hot, right? Right now, our average temperature is 15 degrees. It's very, very hot. It's still essentially boiling. And what does the atmosphere look like? I want to emphasize that the difference between the atmosphere and the land and what's under the land is not what we have today. It's all mixing and going up and down all the time. So no matter what you think of, where's the water, where's the carbon dioxide, where's the nitrogen, it's all over the place. It's up, it's down, it's getting folded in and mixed in. This is just liquid. And it's very non-distinct between the atmosphere and what's in and even below the surface. It's just mixing all the time. So you could say, yeah, the water is locked up in the rock. Well, and then it comes out and it makes steam. Then it goes back down and then it comes back up. So there is not really a way to distinguish much between the atmosphere and the planet. And now as it cools down and the rock starts to solidify, it takes 1 billion years or so for the volcanism to really, calm down. The length of day continues to increase, and we have a kind of 1 billion years here where not much happens. So I have to go through that. Oh, sorry about that. So, because I don't pay for YouTube. And we have a political season coming up. So we have political candidates making all kinds of pleas on YouTube. Now you can see American advertising. Here we go. We got about 1 billion years where it's kind of, is it water? Yeah, it's probably water-ish. It's very steamy. And the water is in the rock and coming out of the rock. And it's there's almost no land here. Okay. The water essentially, and this is let me show you there's another video here I'm not going to spend too much time on, but we can see here this chart, which is not a great chart, but it shows that, can't show the bottom scale. This is 4.5 billion years, that the water vapor rises. And then as it gets saturated and cools, it forms the oceans. And so this is ocean formation here. The oceans are kind of settling in by outgassing steam and then coming back down. And so that takes 1 billion years. And then we start to get, and this land is really just guesswork. There isn't any reason to think that any of this looked like this at all. This is just random little patchy pieces of maybe land and maybe not. Nobody really knows. Certainly it's not accurate to any degree. Okay. And there is no atmosphere, and this particular ice age here is very speculative and may or may not have occurred. If the temperature did go down to 10 degrees, it would have probably be because of orbital mechanics, although there's no atmosphere. So in a minute, we're going to see another glaciation that that may have been actually due to the atmosphere. We'll come to that in a minute. And that's going to be a big freeze. So let's go back to liquid Earth. And pretty soon, and this is kind of, things are pretty boring for hundreds of million years, but pretty soon we get a little action. And this is, some people may know this, this is cyanobacteria. These are bacteria that live anaerobically without oxygen. There's no oxygen in the air. This is probably even wrong. These bacteria thrive in an oxygenless environment, and they pretty much take over. And what happens with these cyanobacteria is they're producing oxygen. Their oxygen is a byproduct, and that interacts with iron and turns the oceans red. And this lasted for a long time. This is called the Great Oxygenization, in which the oxygen component of the atmosphere will really rise a lot. And we'll see it continue to dominate for quite some time until this. This is the Huronian glaciation. Now, this is this is called Snowball Earth. Did it really happen? Maybe. We don't know. Did it happen all the way around? So look at this, minus 28 degrees. Okay, so this is extreme temperature gradient, and it happened, was it frozen ice at the equator? Nobody knows. We're just looking at rocks and drilling holes to figure this stuff out. But the theory is that we went from throwing a lot of, let me go back a little bit. It's not shown here, but there was methane in the atmosphere before this. And it is thought that the methane accumulated and was enough, because there's nothing else in the atmosphere, to keep the Earth hot because of the greenhouse effect. The greenhouse effect is what is keeping the Earth warm here because of the methane, and there's no magnetosphere and there's no ozone yet. So it is thought that the methane is really heating the Earth now. It's not internal heat anymore. It's now solar heat that's being captured and retained next to the Earth by methane. And as we go through this oxygenization, what happens is oxygen and methane combine. And they do when you light a lighter, right? A cigarette lighter. That's methane and oxygen. And they produce oxygen and water. I'm sorry, CO2 and water. Those are the byproducts, is heat, CO2, and water. And it is thought that this has been done chemically for a couple 100 million years and allowed enough methane to be converted to CO2 that the more aggressive impact of the methane greenhouse effect disappeared. And it was the loss of methane, or the kind of eating of methane by oxygen, that created this event, the Huronian glaciation. There's a lot we don't know about it, but it's possibly the only glacial period that really actually was driven by by the greenhouse effect, by the lack of greenhouse molecules for some time, until CO2 and oxygen, until CO2 can build up enough that it starts to have an effect. Now, carbon dioxide here, according to this, is already 1,000 parts per million, which is certainly enough. If this is true, then something else is responsible for the glaciation, because 1,000 parts per million is, all you need is 100 parts per million to have a good solid greenhouse effect that raises the temperature of the earth about 30 degrees Kelvin. So either this is wrong, in which case maybe this was caused by the lack of methane, or this is right, in which case what's causing this is distance from the sun, which is entirely possible. We'll talk more about distance from the sun in other lectures. Either way, it got very cold, the coldest it's ever been. This is the coldest the Earth has probably ever been. And it's very likely, by the way, for you science fans, that CO2 is not in the atmosphere at all, because it precipitated out, because it froze solid. It doesn't freeze solid at minus 23 at zero, but it could have been solid CO2. It could have rained CO2 in the poles at this point. And we know solid CO2, that's called dry ice, right? So it could have had lakes of liquid CO2 and possibly blocks of CO2 ice at the poles. We wouldn't have had that at the equator. This lasted some time until, it's thought that the only way I can really see getting out of this is some process that produces enough greenhouse gas, or enough sunshine just shows up and starts melting away at the equators and then chipping away, year by year by year to unfreeze and unlock. And that's my guess. This is generally how we deglaciate, is by getting a little more sunlight, a little more solar energy. But you have to remember that there was no atmosphere. There wasn't much of an atmosphere here. Oh, no, come on. And so other things are possible that I don't understand. I'm not saying that I'm that clear about it. So here we go back to another epoch of cyanobacteria, which again thrive without oxygen. And I want to show you these guys. You may have heard of them. They're called stromatolites. Anybody heard of stromatolites? These things are all over the world. These are the remnants, the fossil remnants of these bacterial mats that for a couple billion years produced all the oxygen and threw all the oxygen into the air. So all of this oxygen here was produced by those bacteria. And so we're getting now toward the great second big oxygenization event. And this goes on for a long time. This is a boring 500 million years until we get enough oxygen. Now oxygen is starting to climb, that we get bluer oceans and more possibilities for life, because this oxygen is deadly. It's a byproduct of the bacteria I mentioned, the cyanobacteria, and it's deadly to the bacteria. If they have enough oxygen, they'll die, and they do. And so this is kind of the end of most cyanobacteria, and it will be starting a new phase of life that is aerobic. So this is anaerobic, and now we're changing to aerobic. So in a sense, there's this great die-off of all the bacteria floating in the seas that we're churning out oxygen, and we're switching to a new regime where we have bacteria and algae and other creatures, other forms of life that can take in oxygen and breathe out carbon dioxide. And that's the beginning of this. And remember that these continent shapes, didn't happen this way. This is all just made up. It's representational. Maybe it happened something like this, maybe not. I actually don't know I think this is cloud. So I think it's not that hot right now. So we're in technically kind of an ice age here. But remember that the length of day is only 17 hours. So the length of day has a lot to do with things like glaciation. Doesn't necessarily give enough time for the poles to form ice. Also, you have to think about heat. How does heat escape the system? Pretty readily. It can heat enters at the poles and at the equator, or heat enters at the tropics and then exits at the poles via circulation. So there's going to be a lot of circulation poleward here that will transport the heat from the sun. Here we have fungi, and this is just starting to colonize land. Just at about 1 billion years, things are starting to come up onto land. And this is the stromatolite peak. So now we have basically the end of the anaerobes, and we get sex. And so sex and aerobic respiration starts to create a plant-like explosion mostly in the oceans of algae and other plant-like things. What are they called? Lots of, I can't remember the name, lots of small things that can start to photosynthesize and breathe out carbon dioxide while becoming green. And that just starts right in here. The beginning of plants that can have sex, that can therefore differentiate quite a bit and change, that we could have a tremendous explosion here of plant life in the oceans. And now you can see that the oceans are still very open and heat escapes to the poles rather readily, but it's still cold. It's cold and not that icy. And that's pretty interesting. That's probably just because there's so much water that although I can imagine that during this time you have ice on the poles. It's just not shown. It's just normal, but it's not to the degree that it's an ice cap. I'm not sure. So this is a time I don't know much about. Now we're coming though into the age of land animals and plants. And now by 750, now life really starts right here. Now we get land plants and the sea creatures. And so we're going to see here, right here, that we start with an ice age that was almost certainly caused by orbital mechanics. This ice age was most likely caused by something we're going to talk more about later, the Milankovitch cycles, where you don't even have to be a lot farther away to create an ice age. You need to have if the distance to the Earth is the same, so if your orbit is very circular, not elliptical, but circular, and the axis is quite up and down and not tilted, you don't get enough time to clear the ice each year, and ice can grow, and that can allow a glacial period. And whether this glacial period extended all the way and froze the oceans, we don't know. It's not as cold as the last one. But I think most people think, and there's hardly any evidence, so it's just guesswork, that the oceans did not freeze in the tropics. Cold, yes, certainly uninhabitable for most life, but now it starts to come back. And yes, then there's the second, this is 400 so this is 640. So there's going to be another one of these too later, pretty soon. So things are still relatively cool. And just because of the temperatures, not that much happens with life. We do have biodiversification, and it's mostly small things, multicellular organisms that haven't gotten very big. And now after that glaciation, things start to heat up. And here is where life starts to explode. So we get the first trilobites, we get bone, well, we get shells, we get legs, heads, eyes. This is the Cambrian explosion. So much of it is happening in the oceans. We have predators, we have locomotion, we have fins, and we have fish crawling up out of the oceans and into land. And it's all because it's nice and warm. And that gives us just kind of the perfect environment for life to thrive. Carbon dioxide at this point is probably around 5,000, 4,000 to 5,000, 6,000 parts per million. Certainly could have been more. And oxygen, you can see, is up to 16%, right? And why? Because of the plants. Because the plants have colonized. The plants have taken over from the oceans to the land. And that's what's driving this oxygen explosion here, the great oxygenization here. And we will see that this is just on its way up. And that will allow so many more types of creatures. Here we have jaws coming along. We have backbones, skulls. A lot of really interesting things are happening. Here we get sharks and octopuses around this time. And one of the things to realize is that the land doesn't look anything like today, and it gives pretty clear path to let go of heat at the poles. So this is a time of a medium, fairly flat temperature gradient. Does that make sense? So from the equator to the poles, not much change in temperature. Some change, but it's a fairly flat gradient, and it's not a tremendous difference from the equator to the poles. And that's a fairly stable condition that gets interrupted later. Here's some ice ages. Again, this is all speculative, but more or less, we get the basic idea. And now it's cold. Now we see ice caps year round for a couple million years. And this is because of orbital mechanics. This is the distance of the sun to the Earth, pretty much plain and simple. On long-term time scales like this of millions of years, it's all about the distance of the sun to the Earth and a little bit about the angle of obliquity on long term. Now here are the dinosaurs. So now we're getting into this should be the Jurassic. And then the coming toward what's after Jurassic, then something, then Triassic. So we've got insects, 160, 158. Now we're getting towards almost into the Triassic. Cretaceous, we're in the Cretaceous now, but now we're just moving over. And now you can see, recognize any of this stuff? Now we can start to see some familiar territory, just as we're moving from the Cretaceous into the Triassic period, just at the 100 million year time. And now we're going to see here the rift opens up, and this is the Atlantic Ocean here. The North America is divided. These are the Rocky Mountains we can see over here. These will become the Great Plains. And I'm going to show you this a couple of times in a couple of different ways. Watch as we see Africa this is the Rift Valley in Africa is coming together, right? And here's the Mediterranean. This is going to be important for the flow of water. But what is this? This is India. You notice it's kind of missing up here. I'm going to show you a couple things now, because now things get a lot more interesting. So we're at 72 million years. I'm going to stop right here. And we're going to look here. You see, we already have a kind of a big bowl shape. This is the Caribbean Ocean, right? And right here at the Yucatan Peninsula, it's just about to happen. We're just almost there. You're going to see a white dot right here. Ready? There it was. You see that? What was that? 66 million years ago? What happened right there? That was the Chicxulub crater impact by the giant asteroid that knocked off the dinosaurs. So even though it was a tremendously important event for life, the dinosaurs all went away within 20 years maybe, it didn't have much effect on the climate at all. the Earth recovered pretty quickly. On the overall climate terms, it had really no effect. It was washed out by later activity. But I'm going to rewind. I want you to watch India. Okay, so now let's watch. Here's what will be Australia, I believe, and here comes India. Look how fast. Look how fast it's moving. If you want to make the world's highest mountain, you smash in at high speed, and this creates the Himalayas. Faster than anything else at the time. It's like a race car driving into Asia, and really just this remarkably speedy little mini continent going up and hitting. So here we're going to see the impact again. We're going to just watch right here. There it was. And now the next big event, you can see Africa has come together. You can see right now equatorial flow. Now look, the Earth is spinning. We don't think it's spinning, but it is spinning, right? We don't feel it. And it's spinning this way. Okay. And that means that the Earth is spinning this way. Then the water is sloshing that way up against the incoming Earth. That's called the Coriolis effect, right? Coriolis. And that just constantly creates a flow of water, a current of water going the opposite way, coming around in a big circle so that here it's going with the Earth. It's making this big round trip. It's going against the Earth, and then it's coming with the Earth at a higher latitude. And those are the tropic cycles. And there's, that's just at a high level. You got to realize that the water is always traveling west. All right. So we have this flow. We have the flow of water around the equator. The equator is where most of the land and the area of the Earth is. And it's going through the Makassar Straits here and through the open Mediterranean and through the Isthmus of Panama, which doesn't exist. So we have tremendous equatorial flow here at this time at 55 million years. And you notice that it's hot and we have no polar ice. It's a hot regime. This is a hothouse Earth, and that it's fairly difficult to vent the heat to the poles. There's a lot of obstacles here. So the water stays trapped going around the equator. That means this is extremely steamy. This is going to be high humidity all around the world. And that there were, camels and elephants living up at very high latitudes because there's a very, very shallow temperature gradient here from the equator to the poles. Very shallow. The temperature difference isn't that great. So at this point, we have all kinds of land mammals exploding everywhere in a very steamy, jungle-producing environment. Okay, all over the world. And now we're going to come up to the big event that most of your friends don't know about and the IPCC doesn't like to talk about. And it's coming at 33 million years. So we're right about on top of it. You can see that, I'm going to go back a little bit, that the Mediterranean just closed. Here we have water flow. And here comes India. And here closes Saudi Arabia with Turkey. Here's the Middle East forming, and that blocks the incoming water. So now the water has to go this way. And that's why, now you can see why Cape Town has such a mild climate, because the tropical water is coming right down around Africa here. And this is tropical, and this is not. Okay, because most of this water is going to end up going up into the Gulf Stream here. And much of this water will just be immediately cooled by this Southern Ocean. We now start the Southern Ocean. So I'm just going to go forward. Now you see it's 28 million years and this hasn't closed. Let's watch the Isthmus of Panama close right there. You see that? I think that's about 20 million years off on this map. I think you can see it in the temperature record that the Isthmus of Panama really closes at around 33 million years. And this avenue closes. So the whole hydrological pump around the equator stops. And that brings us into a completely different climate regime than we had before. And as soon as, and it's before the Isthmus of Panama closes, right here, when this stops, we get more north-south flow. And the Gulf Stream starts to pump heat up through the Fram Strait here and to the poles so that it can escape, and the Earth cools down. I say the Earth cools down because we've got polar caps coming as soon as these things close. See that? So as soon as we go from a horizontal regime to north-south channeling of water as the Atlantic opens up, temperatures drop because the heat has a chance to escape and deserts form. Everything changes. So if you want to look at the climate from 10 million years before to 10 million years after, everything has changed dramatically around this time when these channels closed up and we started seeing a lot more flow. And that's partly why there isn't, I don't know if that's why there's no land here, but this ocean up here, the Arctic Ocean, is really a heat sink. It's really a reservoir for heat coming up from the Atlantic. And now we got a 24-hour day, and we have ice at the poles year round, and that's an ice age. We're living in an ice age right now. And you can see that it really, the story of the Earth's climate is the story of getting rid of heat. And we're going to spend a lot more time on that because it's not about atmospheric percentages of anything. It's about the movement of heat. So rather than talk about radiation, we'll talk more about heat. And there'll be many lessons and mini lessons about heat as we go. And you've learned some of that with me talking to Mike already. So the one thing I haven't mentioned here is ozone. And the ozone layer formed, and I don't know exactly when, but it was during an oxidization. See, as the oxygen grows from 8%, 9, 10%, as oxygen grows, there's a chance for it to create, as we get in here, there's a chance for it to create ozone, and then the ozone will make its way up here, and the high altitude oxygen will become ozone. And this ozone layer, which is in the stratosphere, so it's about 10 to 50 kilometers up, changes a lot of things about the properties of Earth because it protects. It's not a thin little layer. It's a thick, heavy layer, although it's light up there. There's a lot of ozone, and it protects the Earth from harmful ultraviolet rays. And so that lets a lot of life happen that couldn't have happened otherwise. It also lets a lot of the climate stuff happen that couldn't have happened otherwise. So we'll be learning a little bit more about ozone and the stack, the gradient, the temperature gradient from the Earth to space, which you've learned a little bit already. But that, and then the kind of the final piece of this puzzle is the magnetosphere, which is caused by all the iron turning in the Earth. And the magnetosphere, all the magnetism around the Earth shields us from cosmic rays and from the solar wind. And the solar wind would just take material off our planet the way it does with Mercury. And Mercury is just constantly being eroded and the materials being carried off. That magnetosphere protects us from that. And so those two things are always acting invisibly to protect Earth way up in the stratosphere. All right, so that's this basic lesson on the first, on the history of Earth. Let me ask if people want to ask any questions.
For me, that was very interesting. Actually, I really, really enjoyed that. Thank you.
Good, thank you. I'm glad. I want to try to make it. I talk fast, and the point was not for you to remember everything. If you have one thing to remember from that, it was somewhere around 30 million years ago, the plate movements blocked the flow around the equator and created our north-south orientation of our currents, and that gave us that gave the Earth a chance to cool down from where it was when the dinosaurs were around. I also didn't mention the Southern Ocean about 20 million years ago just became this ring of water that just constantly circulates going westward. And it doesn't have anything better to do than stay cold and not have anything to do with the rest of the planet. It's actually very hard to move heat across this Southern Ocean. And most of the way it happens is through storms above ground, above the ocean. Mostly it's through weather storms that move heat to the pole where it can exit. And so we have now about 5% of our excess heat comes out the bottom through Antarctica, and 6% comes out up here where there's more water and it's better for channeling heat out to space. And we will learn much more about that. That's the heat pump. So this cold Arctic Ocean is very much a remnant of the fact that there's a gap there, and the water just keeps going around and around and stays very cold. Yeah.
Question. I'm just trying to get my head around how the heat escapes at the poles if it gets up there. But at the same time, this affect north-south currents can bring the heat from the tropics to the poles, and that cools down because the heat escapes. It cools down the Earth. But I just don't understand why, if you don't have that current and all the currents are still able to go around the equator, why wouldn't the poles be ice?
Because
they don't have heat coming up that way.
Because the temperature gradient at that time, under those conditions, under that tectonic regime, was very flat. So the difference between the temperature of the tropics and the poles was very low. So they were almost the same temperature. That's why I say it was practically tropical up in northern Canada where the land was. There were camels. The temperature was very warm. Why? Because the whole planet was very warm, and that much of the effect was just to saturate the atmosphere with water, and to try to put out the planet is sort of trying to make as many clouds as possible, which reflects the most sun, but the shape of the continents is what really drives here. So you could say, well, there's this balance between the clouds and the incoming sunlight, the temperature. But really the Earth, and this is maybe kind of the key for this lesson, is that the Earth is always having to get rid of heat, that the heat from the sun is always roughly the same, but the shapes of the continents and the currents create the channels through which that heat can escape. And if it gets blocked somewhere, then it has to go around. Because whenever you have a stick with a hot end and a cold end, the heat has to find a way to get out, right? The heat is this conduction, right? The heat will find a way out. And so it finds its way out according to the obstacle course that is the land. Because most of this heat is going into the oceans. The oceans drive our climate.
Yeah. Okay.
Right. And so in another 10 million years, it could be completely different. And it would have some other mechanism for getting the heat out, right? Because it can't build up, right? If you've got a planet, the one good thing to understand, I'm going to have to carry this on into another lesson, is that the Earth is kind of never in equilibrium. It's always getting colder or hotter. And just for some moments, it might be slightly less getting colder or hotter, but it's always kind of going, a little bit like you're walking. as you walk, you're always out of balance and catching yourself, right? So sometimes it's going toward an ice age, and sometimes it's going toward a hothouse. And on a kind of year-to-year basis, there isn't much change, right? But as the conditions of the continents and the flow changes, the currents and the heat movement have to adapt to that. Now, you can imagine designing the Earth in such a way that you just trap maximal heat and it would get incredibly hot, but still there's a limit to that, and it's going to find a way out around those obstacles at some point, because it has to be in equilibrium, because it's not going to boil. The oceans are not going to boil away. There are all these, there's heat transport mechanisms to solve this problem. And that's where we are right now. It just so happens, right? We just happen to be having universities and grants for people to study things getting warmer when they're getting warmer anyway, and we're still in an ice age. We are in an ice age right now. I hope you have that gives you some appreciation of that. Other questions? Anybody?
Oh, hi there. Yeah, obviously it's quite an interesting sort of history lesson of the formation of the Earth. I'm just a little skeptical. What sort of evidence is there for how old the Earth is? Obviously they said so many billion years, but what actual evidence is that the Earth's as old as they say it is?
Well, we could find rocks that are, I think, 4.2 billion. There aren't very many of them, but we found some of them.
But how is that determined that the 4.5?
I'm pretty sure that's going to be done through
carbon
isotopes. So that there's this half-life of radioactive isotopes and so forth. Some of them are very long half-life. And it's really a puzzle to put together, because you're trying to just coordinate it with other things that and we certainly might be wrong, but I think we're getting a lot better that the Earth is 4.6 billion years old. The universe is 13.7 billion years old, and the sun formed just about at the same time as the Earth, and most of the other planets formed just about at the same time. So you can look around at a lot of different lines of evidence, Kevin, and see that they tend to converge on roughly the same thing. We might turn out that that's wrong, but my guess is that we'll just know more finely, rather than saying, oh my gosh, it's actually 3.3 billion years old. I think we're probably going to end up that it's somewhere in that ballpark.
Okay, thanks for your answer.
And by the way, anybody who wants to do research projects, I've already put one up. Why are the rocky planets at the inside, and why are the gas giants outside? Because there are solar systems we can see where the gas giants are inside. So what's going on? That's not a general rule that the rocky planets are inside. What's going on? We've discussed it a little bit. You can ask GPT about it, and it's still, I would say, a pretty open question, the mechanics of these disks that form as a star forms. What's going on with the material around a star as it forms? I expect that's an area of research, but I don't know how active, and anybody who wants to look into that is welcome to. We can have little study groups, that can work on things and then can present to the group. Whatever you're interested in, tell me or tell the group, and let's try to form a little study group around it, because I don't have the answers to most of these questions. Anybody else? We'll wrap up unless there's another question.
Yes, Dave, I've got a question.
Sure.
It's not so much related to tonight's one, but it's related to the whole carbon dioxide thing. I'm 67. So in the course of my life, I think, say from reports, there's been at least 3 major volcanic, eruptions going on, saying all that time. And supposedly it's possible to sort of calculate how much, as we as humans, since the Industrial Revolution, we have created carbon dioxide from our activities. And it's also possible, say, to calculate when there's a volcanic, say, eruption, there is carbon dioxide emitted,
Oh,
and
yeah.
it's possible. But it seems like, say, one of these eruptions throws out more carbon dioxide than all of our activities in the last 150 or 200 years. So doesn't that sort of put paid to this sort of climate question? If we're having volcanic eruptions that are chucking out more than we've ever done in the last 150 years, say in the course of a week or a month, then like say the debate's over. Carbon dioxide is not a problem, you know?
Certainly a question for all those people who are working hard on carbon capture.
Okay. Yeah. Okay. Well, that was my question. As I say, it's not really.
I don't think it's true. My understanding, Martin, is that the amount of carbon dioxide produced in all of the volcanic events in a year isn't that big. It's not that much compared to what humans produce. Jim, you may have read any papers on this, but I haven't seen anything that told me what you just said, which is that the carbon dioxide from outgassing from volcanoes overwhelms the amount being produced by, and it doesn't affect climate either way, but it's an interesting question. Don't know.
Okay, that report.
Maybe Jim might know something. Do you, Jim?
Well, not much, but I don't think the CO2 emissions from volcanoes is that big in the whole carbon or CO2 in the atmosphere, and that can be verified, in fact, in the Mauna Loa data, and looking at the Pinatubo, is that the correct name of the volcano? In 1992, you can see a blip, but it's not a big blip.
Yeah.
And of course, the other part of the whole question is that the total CO2 in the atmosphere is a mix of perfectly natural carbon cycle,
right,
as well as only 5%, I think, of it is man-made. So it's a matter of proportion and the amount of man-made CO2 in the atmosphere.
Yeah, I firmly believe that somewhere between 0 and 100% of all the CO2 in the atmosphere comes from humans. I have no idea how much.
No, I think even IPCC put it around 5%. So that actually, as well.
I've seen so many papers on this. I've got a collection of papers on this, and they all say different things. So I don't know.
Yeah, we don't know.
The more you study this, the less certain you are.
Yeah.
Okay, as I said, my that report came from a newspaper report, and we all know how reliable.
Yeah, I don't think it's even close. And then we can also discuss heat from volcanoes, which is also turns out to be negligible.
Okay. All right. No, thank you. Thank you.
Sure.
Well, general advice is not to pay too much attention to newspapers or television stations.
Well, or even most public peer-reviewed research isn't very good either. That's our problem, right? If you really want to find out, it's still really, really hard.